start this recording here. Okay, so I was making promises I couldn't keep. Well, I guess I could have. I didn't. So we will do 4.1 today. And then on Thursday, we're going to do 4.2 and 4.3. And then on Tuesday next week, we'll do 4.4. And then on Thursday next week, we're supposed to do 4.7, but we'll probably end up doing more review for test number 4. All right, because so test number 4 is on 4.1 to 4.4. So that's why I'll kind of like, we're supposed to start 4.7 that day, but I think we'll have enough time to cover it the following week. So I think we're okay. And then the next Tuesday, we'll have test number 4. We'll talk about how that's going to work. And then on the last Thursday, we'll do 4.7. Yeah. So we're not doing 4.5 anymore. Not doing 4.5 anymore. And that was just curve sketching. So I think we're all pretty happy about not having to do that explicitly. But I mean, we'll talk about maximums and minimums today, and then we'll kind of keep talking about just characteristics of a graph. So we'll still have all those ideas, but we won't do the actual sketching. So that's in 4.5, but we're not doing it today. So we're marking test 3 right now for you guys, Steve and I. And so once test number 3 is marked, which should be later today, hopefully, you will receive, or you will get, because I always flub how to spell receive, you will get an email. An email from Gradescope to your My Okanagan email. Okay. So this is where you'll be able to just kind of review your test. It'll have kind of comments, and then if you want to have a look at your test, then you've got it there. At least, so that's how we're going to be able to hand those back. It's also how you'll be submitting test 4 and the final exam. And so what we're going to do, and I'll send out an email later, of course, but there's going to be kind of a bonus assignment. Where you have to submit submit a document, and we'll specify what that document is. So submit a document on Gradescope for practice. And then we will use Gradescope for tests 4 and the final. Okay. And so it's really just a way where you can upload your documents, but also if you're writing on paper, you tell me where question 1 is, for example. You tell me where question 2 is, and then it just kind of feeds it to me, and it makes it a lot easier to kind of see and mark, and you're able to make sure that I see all your work and that kind of thing. So so it's just kind of more foolproof, and then you'll get the feedback back through Gradescope. Okay. with all this kerfuffle and things, we are going to have to rejig the grade scheme. And so for the new grade scheme, I guess I should say that. New grade scheme. Oops, if I could spell here. Worse than usual. Labs are going to be 15, and I actually cannot, let me pull it up here. Can't really remember what it was before. Let's see here. Labs used to be 10, and so here used to be 10%. Assignments in the new grade scheme are 20%. And so I'm a little bit, I'll talk about those assignments later because they used to be 10%. And then the tests are still 40%, which was always the case, right? But now the final is worth 25% instead of 40%. Okay. So here, this is the one that I'm most concerned about, your assignment grade. Because I think what some people were doing was they were saying, okay, 10% of my grade, I don't really care about that. So I'm just not gonna buy WebAssign and I'm just gonna go with it. And even if you've kind of been slipping behind on the assignments when they were worth 10, that's not really a big deal. But now we're throwing this curveball and making it 20%. So I do want to give you an opportunity to recoup those grades. Okay, so I will reopen assignments. For you to do, oops, or I guess for you to catch up if needed. Okay. If you haven't gotten a WebAssign account, then please just talk to me and we can figure something out because things got weird here, right? So if you do not, do not have WebAssign, email me. Okay. It's okay. I mean, I don't care either way, but if you don't have it, I want you to have those grades. And so just send me an email and we can figure it out, right? And so there's a couple of different options that we have. So, and just remember, I want you guys to have the best grade possible, right? So just get in touch with me. I know this is kind of different, but for what is essentially going to be an on your own final, we can't have it worth 40% of your grade. So that's why we're shifting things around. Okay. All right. So there's kind of more on the assignments later. I'll send out an email because I'm pretty sure that it's still just, let's see, just the 3. Oh, wow, look at us. It's a few of us. Oh yeah, so for the labs, oh thanks Kobe. The labs will be just the grade that you currently have. So again, if that's a concern, right, so current lab grade. if that's a concern, which I can see, if it is, then just let me know. Okay, I don't have access to your lab grades yet, so because they come from your lab instructor. And so, but if you think that that's going to be a concern, then let me know and we can talk about that too. Okay. All right. So I'm guessing any questions before we start this thing? All right. So like I said, basically any concerns, just email me and we'll get you sorted out. Right. It's not the end of the term. We can still handle it. So like I said, I never did make this video. So, but now because we have time, we're just going to do 4.1 today. So maximum and minimum values, which you would think would be kind of a an easy topic, but it's actually a huge field in calculus because it's used in optimization. So calculus is used in optimization. And optimization is a huge field of math, and things like, well, if you want to maximize something or minimize something, usually these have economic, flares. If you want to maximize profits or minimize costs or both. Subject to constraints, right? So imagine you're running a factory and you've got so many man hours and you've got so many machines and you've got so many, so much material and just so many things that you can use, so many hours in a day even, right? We're limited. So those would be our constraints, but you still want to maximize your profits, right? You want to run your machines as much as often as possible, but if they're expensive to run, right, then you want to maximize those and minimize the cost. So so all this idea of minimizing or maximizing something is optimization, and optimization is a huge field in math. So this is kind of your first step into optimization. So first thing that we want to talk about is, is just some terminology. So there's such a thing as an absolute max or an absolute maximum, which, I mean, honestly, I think you guys are okay if I just write max, but absolute maximum of a function at x equals c, so some point c, means that f of c is larger, so greater than or equal to all the rest of f of x. So for all x in the domain of f. Right. You know what a maximum is, right? It's the largest number. But just how we say it mathematically, right? We have to determine it mathematically. And so f of c, if the maximum is at x equals c, then f of c is larger than all the other f of x's. Same thing for the absolute minimum. The absolute minimum, oops. Same idea of a function at x equals c means that f of c is less than or equal to all the other f of x's for all x in the domain of f. So these are what we call the absolute maximum and the absolute minimum. Okay. If we think about something like a curve like this, maybe, that starts here and kind of goes and ends here, okay, then this is my absolute minimum, right? And this is my absolute maximum. Right? There's no other point on this curve that's smaller than this value or larger than this value, right? So those are my absolute max and mins. However, there's also a type of maximum here, right? That's the highest point around that area. And then there's also a type of minimum here, right? And so what we call these local maximums, and this is a local minimum. Okay. And so if we define those, we've got a local max at x equals c, right? Just using c as a general kind of check-in point means that f of c, not f of x. F of c is greater than or equal to f of x for x near c. Right? So if we imagine kind of, let's see, so here around this point, right, for x near c, we've got this maximum here. Okay, so not overall, but just for any x near c, then we've got a local maximum if that's the largest point. Same thing for the local min. At x equals c is if f of c is less than or equal to f of x for x near c. Okay. So here, what we're saying is x near c, right? If that's c, I guess if I put it on there. Okay. So there are some other situations that we kind of keep an eye out for. There are situations where we don't have an absolute max or an absolute min. And so one situation might be if we have a graph that might look like, whee! Maybe we have some sort of vertical asymptote. And maybe here we have some horizontal asymptote. Here, there's no absolute min because it just keeps going and going and going, right? It's approaching the asymptote. And here, there's no absolute max because it's just running along that vertical asymptote. Another situation would be if we have something like this. So we've got this point, and then maybe it loops up here, but it's open-ended. And then, but at that same value of x, we've got a closed dot, and then it closes. And let's say that this is A, C, and B, only because usually we say that the domain is closed from A to B, because it's included A and B on both sides. So here, this point here, that's your absolute minimum. Yeah. This would be our maximum, right? But it's not our absolute maximum, the points close to it, because this is not a point, right? It's an open dot, and so it doesn't actually exist at that point. Here, this is the value at C. Okay, so here we actually say that there's no absolute max for this function. Okay. So, all right. Let's see here. Oh yeah. So from here, we can talk about the extreme value theorem. So we call these max and mins, we call them extreme values. And so the extreme value theorem, says that if f is continuous, so that is something that we're going to need to check, right? We have to assume that f is continuous, so we have to make sure that that's true. On the closed interval AB, then f attains an absolute max and min, attains an absolute max and min for some values in the closed interval AB, which is just kind of, I don't know, straightforward, I guess. If you've got, I mean, should be pretty obvious. If you've got a continuous function, then it will reach an absolute max or an absolute min at some point if it's continuous on some closed domain. So, I mean, it's a good, important theorem, but it should be pretty obvious. So one thing to keep in mind is that absolute max and min values, or I'll just do max slash min, occur at A, B, or some interior points, right? So either at the endpoints or interior points, right? That doesn't leave any other options, but that's a fact that we're going to use. So let's see here. We're going to follow it up with Fermat's theorem, which says that if f has a local max or min, if f has a local max or min at x equals c, and if the derivative at c exists, right, that's assuming that it's differentiable at c, then what are we saying? Then f prime at c must be 0, right? So here, this is saying that f is differentiable at c, so if f has a local max or min at x equals c, and if the derivative exists, then the derivative must be 0, which we've seen, right? We've seen these graphs here, and we've used the fact that at the peak, right, f prime of c is 0, right? And so that's Fermat's theorem, that essentially if you've got a maximum or a minimum, the derivative at that point is 0 if the derivative exists. Okay, so we actually find that there's 2 different types of these maximums or minimums, but I'll just put a square around Fermat's theorem for now. Okay. Another option, right, is if you have some sort of graph that looks like this. So we start here at A, and maybe it ends here at B. And we've got this. This is an absolute min. Absolute min. But we know at this corner, right? We know at this corner, if I try to draw, oh, let's use a different color here. If I try to draw my tangent line, right? This is saying that f prime at c does not exist, right? And so there are 2 different options, and for these maximums and minimums, local, absolute, max and mins, we call them, just in general, we call them critical numbers. And so a critical number of a function f is a number c in the domain, and we've just been using c as some point in that interval where it's continuous. C in the domain of f, such that the first option is that f prime of c equals 0, right? This is by Fermat's theorem. And we call this type 1, just to differentiate the 2, because the other option is that you have a critical number where the derivative does not exist. And so you would say it's not differentiable. We call this a type 2. So these are what we call the critical numbers, and the type 1, type 2, they're the ones that we want to keep an eye out for. So the critical numbers are what we're trying to find, and we always have to check both types. So local min / max values occur at critical numbers or endpoints. So local min or max values occur at critical numbers. So, and remember, the critical numbers are where the derivative is 0 or the derivative does not exist, right? Type 1 or type 2. So occur at critical numbers or endpoints. There are situations, if we think about, so if I just put a little warning here, right? If we've got something like y equals x to the 3, right? You've got something that looks like this, y equals x to the 3. And we find dy dx, so the derivative of y with respect to x, I get 3x squared. And well, 3x squared, so if I set the derivative equal to 0, then at x equals 0, I'm going to find that the derivative is 0, right? And so at x equals 0, dy dx is 3 times 0 squared, which is 0. Okay. So x equals 0 is a critical number, which maybe I should put it up where I defined it, but usually critical numbers, we'll just write Cn. Okay. So x equals 0 is a critical number, but there's no local min or max. It's just where it's crossing, right? It's just switching from what is it, concave, convex? Can't remember. Anyways, so but no local max or min at x equals 0. Okay. So there are situations, right? But x equals 0 is still a critical number, but it's not a maximum or a minimum. So let's do an example where we have to find the critical numbers. Let's see. Use this page break here. Example. Find the critical numbers of g of x equals x minus 1 over x squared minus x plus 1. So remember, the critical numbers are either at when the derivative is 0 or when the derivative does not exist, right? So we have to check both type 1 and type 2. Okay. But first thing, both of them involve the derivative, so we're going to find the derivative first and then sort out the type 1, type 2 critical numbers. So first thing we have to do is find the derivative here, and we should be pretty comfortable with the quotient rule by now, right? And so we've got g, which is x squared minus x plus 1 times f prime, which is 1, minus f, which is x minus 1 times g prime, which is 2x minus 1, all over g squared, x squared minus x plus 1 squared. We have to simplify this thing, and that might actually be the most work for all these problems, right? The derivative won't be that terrible. It's more the simplifying that might be tricky, so, or not even tricky, just tedious. G prime of x, if I simplify, all right, I've got x squared minus x plus 1 minus 2x squared minus x minus 2x plus 1. I'm just going to leave the, oops, plus 1. X squared minus x plus 1 squared in the denominator. And I get, so if I just kind of expand this thing, simplify, I get x squared minus x plus 1 minus 2x squared minus, or plus x plus 2x minus 1. Of course, I'm going to be able to simplify that even more. over x squared minus x plus 1 squared. This puts me at x squared minus 2x squared is negative x squared. Cross those off as I go here. Minus x plus 2x. Doom, doom. Puts me at plus 2x. And then 1 minus 1 goes away. So now I've just got negative x squared plus 2x over x squared minus x plus 1 squared. Okay, so now we've got our derivative, we've got it simplified. So now we have to find our critical numbers. Find the critical numbers. So the type 1 is when, I guess I shouldn't use f, we're using g prime. Is when g prime of x equals 0. So this thing, g prime of x, well, that can only equal 0 if the numerator is 0, right? Because we can't divide by 0, so it has to fall on the numerator to be 0. So if we've got 0 is negative x squared plus 2x over x squared minus x plus 1 squared, then we know that 0 must be negative x squared plus 2x. I can factor out a negative x, so I get negative x times x minus 2, not plus 2, minus 2. And so here, my critical numbers are at x equals 0 or x equals 2. X equals 0 and x equals 2. Okay. What I'll do is I'll just scoot this over so I can have them side by side on the same page here. So that's for the type 1. In fact, I'll put them here. Let's do the type 2 over here. Type 2 is where the derivative does not exist. This is really only going to be a problem if you have some fraction or a root or something like that. So just like the domain usually. So what we need, right, is over here, g prime of x does not exist if x squared minus x plus 1 squared equals 0, right? If we're dividing by 0, then the derivative does not exist at those points. Okay, so what we do is, okay, well, we've got x squared minus x plus 1 squared equals 0. I can take the square root of both sides. The square root of 0 is 0, so then I get x squared minus x plus 1 is 0. And then, so now I've got this quadratic, which I can solve using the quadratic formula if I want. Negative b, which happens to be negative 1, plus minus the square root of b squared, so negative 1 squared minus 4, a, which is 1, c, which is 1, oops, over 2a, which is 1. So x is 1 plus minus, and I get 1 minus 4, which is negative 3 over 2 here. I can't take the square root of a negative, right? So no real solutions. Therefore, no type 2 critical numbers. Right. So that's fine, that can happen. We still need to check it though. So our critical numbers, right, the ones that we were able to find are just x equals 0 and x equals 2, right? The type 2, there are no type 2 critical numbers, so these are our only critical numbers. Nice. Just make sure I'm not missing a chat or anything. Okay. I'll just head down here. All right. Let's do another example. Find the critical numbers of f of t equals the root of t over 1 plus t squared on the interval, the closed interval from 0 to 2. First thing I'm going to do is I'm just going to rewrite this root t as t to the 1/2, because I know I'm going to have to take the derivative here, and so it's just going to be a lot easier if it's just written as t to the 1/2. You don't have to, but I find that it's easier. Right, so we're finding the critical numbers, which means we first have to find the derivative, figure out where the derivative is 0, and then figure out if there's any places where the derivative does not exist, right? And those would all be our critical numbers. So keeping in mind now, right, that we're on this interval. So our critical numbers must be in this interval, is what that means, right? Otherwise, they're not going to be critical numbers that apply to us. They are for the whole function, but not on this interval. First thing we're going to do is we're going to find the derivative. Okay, f prime of t, so again, we've got this quotient rule, and I've got 1 plus t squared, and then t to the 1/2 puts me at 1/2 t to the negative 1/2 minus t to the 1/2 times 2t all over 1 plus t squared squared. Notice that I won't actually do anything to simplify the denominator. Most often I won't, unless you know you've got the square root here and you're squaring it, then there's an obvious simplification there, but usually I just leave the denominator as it is. And so let's see here. Oh yeah, I guess I didn't tell you, they've added this fancy pointer to Notability, so pretty fun. For me, maybe, I don't know, not for you. All right, so what I'm going to do is I can factor out a common t to the negative 1/2. You have to be careful though, because we've got t to the negative 1/2 and t to the 1/2. So when we factor out a t to the negative 1/2, right, times 1/2 times 1 plus t squared, oops, minus t to the 1/2 minus negative 1/2, right? So factoring out that negative 1/2 times 2t, right? Just kind of emphasizing that this is where it came from. So what I get here when I factor out a t to the negative 1/2, and I guess this is all over 1 plus t squared squared, I get t to the negative 1/2, and then 1/2 1 plus t squared minus, and t to the 1/2 minus negative 1/2 is just t, right, times 2t. I want to get, I've got this over 2 here. Oops. There's a bracket. So I want this over 2 here, and I want to put this over 2. So what I'm going to do is I'm just going to multiply this by 2 over 2 to get that common denominator. And of course, don't forget the denominator here, plus over 1 plus t squared squared. Okay, which is t to the negative 1/2. 1 over 2 times 1 plus t squared minus 2t times 2t, let's say, over 2. Over 1 plus t squared squared. So now I can factor out a common 1/2 here. 1/2 t to the negative 1/2 times 1 plus t squared minus basically 4t squared over 1 plus t squared squared. Now this whole section I can bump down to the denominator, right? The 1/2 I can rewrite in the denominator, and then the t to the negative 1/2 just becomes t to the 1/2 in the denominator. So what do I have here? I get 1 plus t squared minus 4t squared over 2t to the 1/2 times 1 plus t squared squared. Simplifying this just a little bit, right? We've got the 1 plus t squared minus 4t squared, so I get 1 minus 3t squared over 2 root t, just rewriting it as a root, times 1 plus t squared squared. Okay. Yes. And that would be, I would say that's as simplified as we need it to be. So now find the critical numbers. Okay. We'll start with the type 1, which is where it's f of t, yeah, where f prime of t equals 0. So again, we've got this fraction, so f prime of t is 0 when the numerator is 0. And so we've got 1 minus 3t squared, right, equals 0. So we've got 1 is 3t squared, 1 over 3 is t squared, and so t must be the plus minus root of 1 over 3. So t is either negative root 1 over 3, or t is positive root 1 over 3. The root of 1 over 3, let's see here. Root of 1 over 3, whoops, lost it. So this is roughly negative 0.577, and t is roughly positive 0.577, right? Remember, it has to be in the interval, and the interval that we're interested in is between 0 and 2, I want to say. Yeah, so 0, 2. So this is a critical number, but it's not in the interval 0, 2. This one is fine, right? This one's good. So t equals the root of 1 over 3 is a critical number. That's for the type 1s. How about for the type 2s? Type 2 is where the derivative of f of t does not exist. So that's when we're dividing by 0, right, in the derivative. And so looking at the denominator now, we've got 2 root t is 1 plus t squared squared. Where does this thing equal 0? Well, it equals 0 if t is 0 here, right? And then here, the other option would be if this is equal to 0, 1 plus t squared squared can never be 0, right? Because t squared is always positive, and so 1 plus a positive number squared can never be 0. And so, therefore, no solutions to this side. But t equals 0 is a critical number. So t equals 0 is a critical number. So we've got t equals the root of 1 over 3 is a critical number, and t equals 0 is a critical number. Okay. Just make sure. No questions. Okay. Let's see here. So, we've got a method for finding the absolute max and mins, and so we call it the closed interval method. Of course, it only works on closed intervals, but usually that's what we're dealing with anyways. And so the closed interval method for absolute max and min values so the goal here, the goal of this thing is that as long as we have a continuous function on a closed interval, we will be able to find an absolute max or a min. And so given a continuous function on a closed interval, right? So there's a lot of things that have to be checked, right? Is it continuous? Are we on a closed interval? On a closed interval from A to B, we want to find the absolute max or min. Okay, so that's our goal of this exercise here. So the closed interval method is how we're going to go ahead and find just absolute maxes and mins on a closed interval. Okay. So there's a couple of steps that we need to follow. The first one, first one is that you have to find the critical numbers. So find the critical numbers. Find the critical numbers inside the interval the open interval AB, right? So not including those endpoints, right? And remember that type 1, the first type that you're going to check for is where the derivative equals 0, right? And then type 2 that you're going to check for is where the derivative does not exist. second thing you're going to do, right, because we had that theorem, right, that the max and mins occur either at the critical numbers or at the endpoints. And so the second thing that you're going to do is you're going to evaluate the function, or I guess we have to evaluate the function at the critical number, and then we evaluate it at the endpoint. The order here doesn't really matter, but I was getting ahead of myself. So evaluate the function at each critical number. And then evaluate the function at the endpoints A and B. Evaluate the function at the endpoints A and B. And then, so now you've evaluated the function at the critical numbers and at the endpoints. So out of these, you'll be able to pick out which one is the largest and which one's the smallest. And so determine the largest. Determine the largest as the absolute max and the smallest as the absolute min. So this, I'm going to try to put a box around this, because this is what we're going to use for basically the rest of the class. Oh. Okay. So some key things, right, are that we have a continuous function and we get a closed interval. Then we'll be able to find the absolute max and mins using the closed interval method. So let's do an example. Find the absolute max / min of the function f of x is 2x to the 3 minus 3x squared minus 12x plus 1 on the interval -2, 3, and it's a closed interval. So here, we just want to check in, is it continuous? Yes. All right, this is a polynomial. Remember at the beginning of the term when we were talking about just continuous functions, how do we know them? Well, continuous functions are things like polynomials or sine, cosine, right? Those are all continuous functions. And so maybe have a look back, and because now we're going to be able to, or we need to be able to say that something is continuous, right? And do we have a closed interval? Yes, the interval is closed on -2 to 3. Right. So now we can continue. So the first thing that we're going to do is to find the critical numbers. Find CN's critical numbers. Finally, an easy derivative, right? Just a polynomial. And so we've got the derivative of f is 6x squared minus 6x minus 12. And my type 1 critical numbers are when the derivative f prime of x equals 0. And so I've got 6x squared minus 6x minus 12 equals 0. Again, I've got this quadratic, so I can use this quadratic formula. So I get x is negative b, which is negative 6, plus minus a square root of b squared. So in this case, that's negative 6 squared minus 4 times a, which is 6, times c, which is negative 12, over 2a, so 2 times 6. So I get 6 plus minus the square root of 36 plus 288 over 12, which just happens to work out to 6 plus minus 18 over 12, which is 24 over 12, and negative 12 over 12. So x is going to be 2 and negative 1. Remember, we're only interested in values between negative 2 and 3. So both of these are in the interval. So both in negative 2 and 3. Oops, close interval. So therefore both are critical numbers. Okay. Keeping it kind of on the same page, I kind of like the look of that, is where the derivative does not exist. Well, here, there's no point, right? Polynomials are continuous, and so they're differentiable over all real numbers. And so there is no point where the derivative does not exist. And so this is not applicable since f prime of x has the domain of real numbers. So f is, and I should say and f. And f is differentiable over all real numbers. Okay. So the critical numbers that we found were 2 and negative 1. Okay. And so those are our only critical numbers. So the second thing that we're going to do, therefore the critical numbers are at x equals 2 and x equals negative 1. Okay. Second thing we want to do is we want to evaluate the function at these critical numbers, and then we're going to evaluate the function at the endpoints, right? At either the endpoints or the critical numbers, that's where the maximum or the minimum will occur. So if we plug in critical numbers to f of x, at x equals 2, for example, we've got f of 2, which is 2 times 2 to the 3 minus 3 times 2 squared minus 12 times 2 plus 1, which puts me at negative 19. And I get 16 minus 12 minus 24 plus 1. So x is negative 1, so f of negative 1 is 2 times negative 1 to the 3. Remembering that negative 1 to the 3 is going to be negative 1, and so minus 3 times negative 1 squared, that's just going to be positive, minus 12 times negative 1 plus 1 should be negative 2 minus 3 plus 12 plus 1, 8. Okay. These are so far my two contenders for a maximum and a minimum. right? We also have to evaluate the endpoints because we could have something that looks like, well, now we've got a negative 19. We could have something that looks like this, right? And so we could have, you know, a point here that we haven't taken into account. So third step we have to do is plug in the endpoints. Into f of x. The endpoints are at x equals -2. So f of -2 is 2 times -2 to the 3 minus 3 times -2 squared minus 12 times -2 plus 1, putting me at -16 minus 12 plus 24 plus 1, -3. And at x equals 3, I'm at f of 3. 2 times 3 to the 3 minus 3 times 3 squared minus 12 times 3 plus 1, putting me at 54 minus 27 minus 36 plus 1 is -8. Okay. So here, these are my contenders for the maximum and minimums, right? Everything else is going to be either, you know, well, depending on if it's a maximum or a minimum. There's no value larger than 8, and there's no value less than -19, right? So these would be our absolute max and mins. Okay. We had to evaluate the function, right, at the endpoints as well, because they could be the absolute max and mins, but in this case it worked out that the critical numbers give us our max and mins. And so the fourth step, because I'm on a new page here, compare and determine the minimum and the maximum. So what we've got is the absolute min of f is -19 at x equals 2. Because it happens at x equals 2, but the output is -19. So that's the absolute minimum. And the absolute max of f is at +8 when x is -1. Is +8 at x equals -1. Nice. There. That's how it's done. Okay. Let's do another one. If we have to find, let's see here. Find the absolute max/min of f of x equals x times the root of 4 minus x squared on the interval -1, 2, which is closed. First thing you have to check in, right, is it continuous? That's the only way that we can use this this method, the closed interval method. Yes, it is, right? There's no reason to think that it doesn't exist anywhere, right? Has the at least on -1, 2. Okay, so it's continuous. Yes, on -1, 2. And do we have a closed interval? Well, we just said it. Yes, -1, 2. Right. Cool. So you do have to check those, right? That will be a mark on your test for So just make sure that you check those before you go ahead and do your work. So then the first step is to find the critical numbers. Find the critical numbers. First thing I'm going to do is I'm just going to rewrite f of x with 4 minus x squared to the power of 1/2, just to simplify my derivative. And so the first thing I'm going to do is first I'm going to rewrite f of x is x times 4 minus x squared to the power of 1/2. Okay. Here, if I let this be f and this be g, I've got the product rule. So if I use the product rule, the derivative of f, well, is going to be f, which is x in this case, times 1/2 times 4 minus x squared to the negative 1/2. There's a little chain rule in there. Well, I guess I should add that. G has a chain rule, and all together on the outside there's a product rule. Times the derivative of the inside, which is negative 2x, plus, and then we're going to take the derivative of f, which is 1, and then times 4 minus x squared to the 1/2. Now, I'm going to rewrite this. So now our goal is to simplify this thing so that we can figure out where the derivative is 0 and where it doesn't exist. So we get negative 2x squared over 2, and then now I'm going to rewrite this 4 minus x squared as a square root instead. And so we've got square root of 4 minus x squared, right? The negative 1/2 bumps it down to the bottom, or the denominator. Plus, and then I've got the root of 4 minus x squared, just because it's easier to look at. If I need a common denominator here, well, first things first, let's cancel this 2 and 2 so that they're not clouding or making a mess here. So if I need a common denominator of root 4 minus x squared, what can I do? I can multiply this side by 4 minus x squared over root 4 minus x squared. So what do I get here? I get negative x squared over root 4 minus x squared plus 4 minus x squared, right? Because root 4 minus x squared times root 4 minus x squared makes 4 minus x squared over the root of 4 minus x squared. Now I've got that common denominator. So now I've got negative x squared plus 4 minus x squared over the root of 4 minus x squared. Negative x squared minus x squared puts me on negative 2 squared, so I get 4 minus 2x squared over the root of 4 minus x squared. That's as simplified as I need it to be, right? Because now I can look at this and say, okay, wherever this numerator is 0, that's my type 1 critical number, right? Where the derivative is 0. And wherever the denominator is 0, that's my type 2 critical number. And so that's where the derivative does not exist. So finding my critical numbers is definitely the most work. Type 1, right, is where, and this thing was where f prime of x equals 0. Well, 4 minus 2x squared over root 4 minus x squared equals 0, I can multiply that root 4 minus x squared over to the right-hand side. So I get 4 minus 2x squared equals 0. Solving for this, right, I get, well, there's a couple of different options here. I could do 4 is 2x squared. So I get 2 is x squared. So x is plus minus the root of 2. Okay. Remember to always, you have to check in and make sure that both of these are in the interval, right? And so remember the interval that we're interested in is -1, 2. And so x is either negative root 2 or x is positive root 2. So the approximation of the root of 2 is, so x is roughly -1.414, or x is approximately 1.414. Here, right, -1.414 is not in the interval -1 to 2. Right? So this tells me that x equals root 2 is a critical number. How about for the type 2? My type 2 is when the derivative does not exist. The derivative does not exist when the root of 4 minus x squared equals 0, right? When I'm dividing by 0. So I can square both sides and I get 4 minus x squared equals 0. So 4 equals x squared. And so x is plus minus 2. And so here we get x is -2 or x is positive 2. Okay. X is -2 is not in the interval. Not in -1, 2, so it can't be a critical number for this section. X equals 2 is an endpoint. So we were going to evaluate it anyways, but it's also happening to be a critical number. I'll clean this up here. Endpoint. Oops. Oh. So endpoint and critical number. But what we said, right, in our list is the critical numbers are on the open, so not including those endpoints. It's not really important. You're going to evaluate it at the endpoint anyways. But the critical numbers that we're interested in are just the ones not including the endpoints. So the second thing that we have to do is we have to plug in the critical numbers. So the only one that I'm going to do here is the root of 2 is a critical number, and then I'm going to save x equals 2 and use it as the endpoint. Now, I'm not really too picky about that, but it just looks better if you have 2 endpoints because it just makes more sense. And so if we do at x equals root 2 was a critical number, f of root 2, f of x was x times the root of 4 minus x squared. So we've got root 2 times 4 minus root 2 squared. And then that's all square rooted. Sorry, there. This becomes root 2, and then times the root of 4 minus root 2 squared is just 2. So we get root 2 times root 2, which is just 2. Right? So that's the function evaluated at root 2 is just 2. Third thing we're going to do, I'll put it on the next page here. We're going to plug in the endpoints. And here, like I said, you could have just used x equals 2 earlier as a critical number, but it just looks weird if you don't have 2 endpoints because it's supposed to be a closed interval. So x equals 1 puts us at f of -1, which is -1 times the root of 4 minus -1 squared. Oh, I'll put it down here, which is 4 minus 1 negative root 3. And at x equals 2, I'm at f of 2, which is 2 times the root of 4 minus 2 squared, which is 0. So my contenders here for my max and mins, I've got 2, negative root 3, or 0. So it looks like my maximum is when f of x is 2 at x equals root 2. And my minimum seems to be when f of x is negative root 3 at x equals -1. So that's my fourth step, is just summarizing all that. So I've got an absolute minimum of f of x is the negative root 3 at x equals -1. And I've got an absolute maximum of f of x is when f of x is 2 at x equals root 2, is 2 at x equals root 2. Nice. Okay. Wow. Once more, I thought I was gonna run out of time, but that's all we've got, and we've done a good amount of examples here. So what we need to remember from this section is just using the closed interval method like we were doing here to find the absolute mins and maxes, right? So we're just following the 4 steps that we talked about, where we first have to find, we have to find the derivative and use it to find the critical numbers, and then evaluate the function at the critical numbers, and then evaluate the function at the endpoints, and then determine which of those values are the largest and the smallest. And those are our absolute max and mins. All right. Open it up for questions. Let me get back here. Any questions, guys? No? Okay. Give you guys a little bit of time to type it out, or otherwise, that's all I've got for today. I'll not see you, but you'll hear from me on Thursday. All right. Stop this recording here.